Alright, the weirdly named question 1, which is actually something like question 10 of the year 13, 2018 mock. I'm losing the will to live. It's about enthalpy of hydration to unhydrated salt. Look at this equation. MgCl2 solid plus 4H2O gives MgCl2 plus 4H2O. Why can't the enthalpy change of this reaction be determined directly by calorimetry? Well, how am I going to add exactly 4 molecules of H2O to every 1 molecule of MgCl2? That's the problem here, isn't it? The only way I can add 4 molecules of H2O to MgCl2 is to pop some MgCl2 in some water. And then what's going to happen to the MgCl2? Exactly, it's going to dissolve. Some of it will form MgCl2 4H2O, but the majority of it is going to dissolve. So this is not something we're going to be able to do by calorimetry. This is not something we're going to be able to work out by experiment, because the MgCl2 is simply going to dissolve. Fortunately, there's another better way. Look, there's another better way. Calculate the enthalpy change for the absorption of water by MgCl2 solid to form MgCl2 for H2O. So let's do MgCl2 plus 4H2O gives MgCl2 dot 4H2O. And we haven't done complexes yet, but the dot means it's water of hydration. So a bit unfair, I suppose, but you come across that. You should know that. What data are we given in the table? We're given enthalpy of solution of MgCl2. So MgCl2 going this way to make Mg2 plus Aq plus 2Cl minus Aq. That process is minus 155 kilojoules per mole. And we're given the enthalpy of solution for MgCl2 4H2O is minus 39. So turning this stuff into this stuff is minus 39. And okay, you want to get picky about the water. Well, water doesn't dissolve in water, so the water is going, water going that way. Okay, for a 0 change plus 4H2O. So there's the 4H2O. Yeah, okay, all right, super. Now I need to just look at ways around and it's this delta H I want. This is the enthalpy change I want. So I need to look at way around the cycle that don't contradict any arrows, don't go against any arrows. So it's going to be this way and then that way. So delta H plus minus 39 equals minus 155. So delta H equals minus 55 minus 39. So you can work it out. Good. 0. Question 1.3. Describe how you'd carry out an experiment. Describe how you would carry out an experiment to determine the enthalpy of solution of anhydrous magnesium chloride. So what this means is regurgitate for me on the page. Vomit up your method for working for a calorimetry, a basic calorimetry experiment. And it's the enthalpy of solution of anhydrous magnesium chloride. So it's just MgCl2, okay, going to Mg2 plus 2Cl minus. So you need to get your practical folder out and work out how we did this. We're going to have a known mass of that. We're going to dissolve it in water and measure the temperature change. That's the basic method. So we're going to need to work out how much energy is released by that temperature change. So we're going to need to dissolve it in a known volume of water. If we know the volume, we know the mass, and we can work out the energy released for the temperature change for MC delta T, mass times specific heat capacity times temperature change. We're going to need to get our timers out, aren't we? And we're going to need to extrapolate back. It's the old, starting temperature, and then we add and then we measure temperature over time, and we extrapolate back like that to give the temperature rise when we added the MgCl2 to the water. We're going to ignore the mass of MgCl2 in the calculation, in the MC delta T calculation. 6 marks to get, right? So it's as much experimental method as you can remember. It's how we're going to measure the MgCl2, how we're going to measure the water, how we're going to measure the initial temperature over time, how we're going to measure the temperature over time after it's been added, how we're going to extrapolate back, and how we're going to work out the difference like that. Okay, practical folder, go look it up, or look it up in the textbook. 6 marks to get. So how many, so we had one, was there one experimental method or question already in this? Paper 3, this question came from paper 3, and it looks to me that's where you're going to guarantee to get an experimental question. Part 4 is another Gibbs free energy change. So you won't get 2 in the same paper. This came from the paper 3 last year, so it's a mashup because I had to take some stuff out that we haven't done. So you wouldn't normally get 2 things like this. You're asked to plot a graph. Here we go of the free energy change, how the free energy change varies against temperature. And you're going to plot the graph, and I think there's 2 marks for plotting the graph correctly, and it's going to give a nice big line like this, okay, and then calculate the gradient of the line in the graph. So it pretty much walks you through what we're going to do. Now, calculating the gradient of a straight line. Big ups to all the people that took, let's take a tiny bit up, the up divided by that. No, why would you do that? That's insane, right? There. Okay, that's going to give you the most accurate result. That's how I want to see a gradient calculated for a straight line. The maximum up, the maximum height divided by the maximum across, right? I lost it. Calculate the gradient of the line in the graph and how to calculate the entropy change for the formation from its elements, right? So we know that Gibbs delta G equals enthalpy minus temperature delta S. Right, so if we rearrange that, the gradient, the change in Gibbs over temperature equals minus delta S, doesn't it? So our gradient is minus delta S. So our gradient, where could we have gone wrong calculating the gradient? Well, these negative numbers are a bit confusing, but we're going from 602 to 592, so that's getting more positive. So the gradient will be a positive number, so the value for delta S is going to be a negative number. We're going to remember that we've got kilojoules per mole here, but the entropy change is in joules. So we're going to need to times our gradient by 1,000 to get the right answer.